This is John Whitaker for the Mathematical Analysis 1 class. And this is our second lecture. And I want to pick up where we left off, talking about set theory. So we ended last time talking about some specific important sets. And they were collections of numbers. But I want to talk about some generic important sets, too, in particular now. So this is set theory continued. Okay, so two general important sets. One is the universal set. It is denoted by script S and is the set of all elements of interest Then the other set that I want to talk about is the null. That's denoted by the circle of the line slice through it, or empty set. And that's denoted by brackets with nothing in there. Is the set, so they're the same set, is the set that contains no elements. So those are two important sets. What I want to do is I want to look at example where they would come into play. Okay, so as an example, if we looked at the collection, let's define this set to be A. It's the set of all Ohio cities whose population, whose human population, exceeds 1 billion. Okay, so that's that. Then what I want to tell you is the universal set. Oh, the universal set I denoted by script S, but really we denote it by U. Script S is what we use in probability, and I made a mistake there in terms of notation. We usually denote it by script U, the universal set. So the universal set, what it would consist of, it would be the collection of all Ohio cities. So that's the collection of objects that we're interested in. For set A, which is the set of all Ohio cities whose human population exceeds 1 billion, that's equal to the empty set. A doesn't have a city in it. It doesn't have an object in it. Or you can say that's the null set. Okay, so those are examples of empty set and the universal set. Okay, again, I made a small notational mistake here. Let's go back and look at it. Right here, this should have been denoted by script U. Okay? Okay. Well, next, I want to talk about something called subsets. So the definition, given two sets, let's give them names, say A and B. B is a subset of A denoted by B, and then we have this cup on its side with a line underneath it, A, if for each x in B, x is in A. Okay, so to be a subset, for B to be a subset of A, everything in B is in A. Okay? So as an example, if I take a look at the sets A equaling to, let's say 1, 2, 3, 4, and 5, and B is the set equaling to 1, 2, 3, and C, let's call it E, is the set equaling to, let's say 1, 2, 3, 7. Okay? Then here's what I can tell you. B is a subset of A. Everything in B is in A. E is not a subset of A. Okay? So I draw a line through the possibility of subset here. And the reason E isn't a subset of A is because 7 is in E, 7 is in A. Not everything in E is in A. Okay, I'm going to talk about an alternative definition. And to subset, so it says given two sets, A and B, B is a subset of A if there is no element of B that is not in A. So B is going to be a subset of A if you can't find anything. If there's nothing in B that's not in A. Okay? What this definition gives us is a fact. And that is the empty set or null set is a subset. It's a subset of any set. So you give me a set, and then the empty set or the null set will be a subset of it. And the reason is because you can't find anything in these sets that's not in the given set. Because there's nothing in these two sets. So, that's an interesting fact. Next thing I want to look at is what does it mean for two sets to be equal? So, given two sets, say A and B, then A is equal to B, denoted by, this is a shocker, A equal to B, that's how it's denoted. If two things happen, A is, I'll write down this one, B is a subset of A, and A is a subset of B. Okay? So for A to be equal to B, everything in B has got to be in A, and everything that's in A has got to be in B. That's how they're equal. They contain the exact same elements. So as an example, if I let A be equal to, let's say 1, 2, 3, 4, and B be equal to, let's say 2, 3, 4, 1, then A equals to B. The reason is everything in A is in B. 1's in A, 1's also in B. 2's in A, 2's in B. 3 is in A and 3's in B. 4 is in A and 4's in B. And likewise, everything in B is in A. So they contain the exact same objects. What this example shows that in sets, it doesn't matter the order in which we list things, that they can still be equal. So in sets, it doesn't matter how we list the elements. Sometimes it might be advantageous to list them a certain way, but still the same set regardless of how we list them. I want to look at another example. And so let's let F be equal to 2, 3, 6, and 8. And G be equal to, let's say, 2, 3, 7, and 8. Then F and G are not the same. So F doesn't equal G. That's an example of two sets not being equal. Another definition, we've learned about subsets. I want to talk about a particular type of subset relationship. So we say, given two sets, say A and B, then B is a proper subset it's a proper subset of A, denoted by B, and then we have a subset symbol, but instead of just having exclusively the subset symbol, with this line underneath, I put a slash through it. And so if B is a subset of A, but there exists an X in A with X not being in B. So to be a proper subset, everything in B is in A. So B is a proper subset of A. If everything in B is in A, but A's got something that B doesn't have. Okay? Essentially, what we're saying is B is a subset of A, but it's not equal to A. Okay. I would like to look at an example of proper subsets. So let's let A be equal to 1, 2, 3, and 4, and B equal to 2 and 3. And B is a proper subset of A. Because everything in B is in A, but A's got something that isn't in B. Okay. The next thing I want to talk about is operations on sets. So when we talk about operations, we're talking about things that we can do between sets. And the first operation I want to talk about is that of intersection. So here's a definition. We're given two sets. say A and B, the intersection between A and B is denoted by A with this cup going down and given by, okay, so A intersect B is equal to the collection of all objects, X, such that, so I'm doing this in set builder notation, X is an element of A and X is an element of B. Okay. So, the idea of intersection is what the sets have in common. Okay, that's what we're listing with the intersection. And the word associated with intersection is the word and. So to be in the intersection, you have to be in both sets. You've got to be in the first one and the second one. Or if there's a collection of sets, you've got to be in all the sets to be in the intersection. First comment, this second comment. Here's an example. So let's let A be equal to the set containing 1, 2, 4, 7, and 9, and B equaling to the set containing 1, 3, 7, 10, and 11. Then A intersects B. So that's the set of what's in common. So look, is one's in A, is one's in B? Yes, so I'll get to write it down. 2's in A, is 2 also in B? No. 4's in A, is 4 in B? No. 7's in A, yes, 7's in B. 9's in A, 9's not in B. And I've gone through all the guys in A. To be in A intersect B, you've got to be in A, and you've got to be in B. So this is the only guys that are in both A and B. So that's one operation that we have between sets, is intersection. Okay. Another operation that we have on sets is that of union. So given two sets, A and B, the union between these sets is denoted by A union B, and given by A union B is equal to the collection of all x's such that x is in A or x is in B. So to be in the union, and it's indicated with the cup going up, looks like a U. You've got, you're an object that you're either in the first set or the second set. So to be in the union, you've got to be in at least one of the sets. Might be in both. So the idea of union is that it combines the sets together. The word associated with union is or. Sometimes we think of the word plus as well, but or is the more traditional math word that we use. Let's look at an example.